Okay, so next example, at 300 Kelvin, sulfur dioxide reacts with water to form hydrogen gas and sulfur trioxide, and we have a Q value given here as well. And we want to calculate the concentrations at equilibrium if all substances have starting concentrations of 0.50 moles per liter. So we do have our given concentration. So first step is there is our balanced equation, and we're going to calculate our Q value. We're going to plug in all of our 0.5s, and we'll notice that this time it's equal to 1. So our comparison is that 0.1 is less than 1. So we're going to be proceeding to the left. So these ones are going to be increasing here. So let's reflect that in our ice chart. There's our equation. There's our initial concentrations. We're going to the left, so our reactants are increasing and our products are decreasing. And there are our values for at equilibrium. So we can calculate our K. Well, sorry, we know our K, so here's how we're going to do it. We know our K is 0.1, and we got all this stuff here. So I guess another way to write this, because you'll notice the terms are the same here, top and bottom, is we can just simplify it by putting that. Now, what you might notice, and if you're good in terms of mathematics, is that we can actually simplify this expression by doing the square root of everything. Because by doing the square root of everything, we're in essence getting rid of the square root, or the squared signs there. We're really just taking the square root of 0.1 and kind of proceeding. So the square root of 0.1 is 0.316. And notice that we've gotten rid of the squareds here. Now it's just a matter of doing our cross multiplication step. So these two values multiplied by each other, going there, and then this value going here. Collecting your x terms and getting... I left out a few steps there, but it's just collecting like terms and dividing by x, and you get 0.26. So to finish this one off here, we can sub our value in for x, and we get our concentration of the sulfur dioxide, which also is the same as water because they have the same plus values there. And over on the product side, we're going to be subtracting, so we get 0.24 molar for each of those ones because, again, they're the same values. Last one here, in order to study hydrogen halide decomposition, a researcher fills an evacuated 2.0 flask with 0.2 moles of HI gas and allows the reaction to proceed at 453 degrees Celsius, pretty warm. So there's our balanced equation. We're going to find the concentration of everything at equilibrium if K is equal to 0.25. So our plan is that we are going to repeat our well, first thing we got to do is we have to deal with the fact that we don't have a concentration, but we can simply come up with a concentration here. And that's going to be our first step. So there is our concentration of the HI calculated at 0.1 molar. So to reflect our changes there, we've got 0.1, and notice that we've got 0 for the two products because this one has yet to proceed. And so our changing is going to be based on our coefficients here, so 2 and a 2. And of course our products are forming. We don't need to do the KQ comparison because there are literally none to start with, so it has to be forming here. So that's why we've got our plus x's. So there's our stuff. And now it's just going to be plugging in our values and doing our mathematics. You can double check my math. Hopefully I got it right. When I get to this point, I needed to use the quadratic equation solver to get my numbers, and I came up with that for my x value. So I'm just going to go ahead and plug that back in. And again, these two are the same here. So that's why we have that value. So there's our concentration of those. And our HI is going down. So it's a very small one. So this reaction is proceeding to the right.